One day we're gonna live in Paris. I promise.
Alrighty, so what is this? They're basically both the existence and the uniqueness. We're going to be covering these in what are two theorems. The existence theorem, so we could kind of call this a theorem. And then the uniqueness theorem as well. Okay, so for the existence one, we basically start with an ODE, a first order ODE in normal form. So something that looks like this, okay? And again, this is in normal form. That's important. Normal form. Alrighty, and then I'm just going to basically kind of write down the theorem. That's what the important part is to both of these sections, the existence and uniqueness. And then I'll go through and explain each of the parts, okay? So suppose f of t comma x, so this thing on the right side is defined and continuous. So that's important that we have both of those. So that it's both defined and continuous on some rectangle R, on a rectangle R, and I'll explain what this rectangle is in the TX plane. TX plane. Okay? Alrighty, so what is this? I'll just draw a little picture over here. So let's say this is the TX plane, right? And let's say we have some rectangle, meaning that T goes from some interval to some interval, so from like A to B, let's say, and then X ranges from C to D, let's say, okay? So on this rectangle, defined by T being in between A and B, and X staying in between C and D, on this rectangle R, if our function is defined on this rectangle, or inside this rectangle, if it's defined and continuous there, then we have the following. Then given any point, t naught, x naught, so these are actual values, okay? So let's say t naught, x naught's right here. Okay, so this is our point in question. If it's inside, or contained in, this is the symbol that says contained in R, the initial value problem, I'll abbreviate, the initial value problem, IVP, of x prime is equal to f of t comma x, and along with x of t naught is equal to x naught. This is our initial condition now, okay? That point is our initial condition. Then we're guaranteed that this has a solution, I'll just abbreviate, x of t, defined in an interval. Sorry for all of the technicality, but that, like I said, this is the main crux of what this section is about, or the two theorems, the existence theorem and the uniqueness theorem, okay? Is in an interval containing t naught, okay? Also, it's just important to note, I'll just squeeze it in here, this solution that we do find, or that is there, that is guaranteed by the existence theorem, will be defined. So we're also guaranteed that some solution that goes through here, so let's say the solution goes like this or something, okay? So this solution will be defined at the very least, until the solution curve, which is given by t going to a point t comma x of t, okay? That just means that for a given value of t, it gives you a point in the tx plane, leaves R, the rectangle, okay? So that just means, like I drew up here, when we have a solution curve, we're inside this rectangle R, right? This solution curve is only guaranteed to exist and be defined inside that rectangle. Like out here, it doesn't even, there could be like an empty, like a hole or something, or it could just not exist or be undefined or something. But we don't really care because we're only concerned with what's inside of our rectangle R. Okay? Alrighty then. So just in general, I know this is a lot just to look at, but it's basically just saying in a bunch of words that if this side, if our x prime is equal to f of some function of t and x, if that function of t and x is defined and continuous on some rectangle, and oftentimes we don't even have to concern ourselves with a rectangle, and sometimes we do, which we'll come upon in future problems, but then if we're given some point inside of that rectangle, with regards to t and x or anything like that. The initial value problem of this thing here, given our original ODE and this initial condition, has a solution. That's basically all it's saying, okay? And we're only guaranteed that solution inside of the rectangle that we look at, okay? Sometimes, like I was saying, it's not really a rectangle. Sometimes it's just like t is defined everywhere, or the function is defined for all of t, so then our t would go from negative infinity to infinity, and we don't even have to worry, right? So anyways, the important thing is that you just understand the basics of what this theorem is saying, and oftentimes, actually, the existence theorem is used in conjunction with the uniqueness theorem, which is arguably more focused on in this section, as for the problems that you're given for your homework and in the practice problems, okay? So let's move on to the uniqueness theorem now.